Hello, my name is Erion Luga. I am a lecturer and researcher at Epoca University, Tirana, Albania. The topic of my lecture is the importance of durability in reinforced concrete structures. During this lecture, we will talk about concrete, durability of reinforced concrete structures, factors governing concrete durability, processes affecting the durability of concrete, and conclusions. Concrete is nowadays the most widely used material in the construction industry. Most of the structures surrounding our urban environment are made of reinforced concrete. In many countries, the ratio of concrete consumption to steel consumption exceeds 10 to 1, and the total world consumption of concrete in 1 year is estimated at 3 billion tons. Man consumes no material except water in such tremendous quantities. As civil engineers, we are mostly concerned about the mechanical behavior of concrete and reinforced concrete. We must be conscious about the problems rising from the lack of concrete durability. The durability of concrete is very important because concrete should be capable to withstand the conditions for which it has been designed throughout the life of the structure. Loss of concrete durability can be caused by external agents arising from the environment or by internal agents within concrete. Concrete suffers from different causes of deterioration. The effect of these causes may result in loss of strength in the form of different types of cracks, spalling, or surface wear, etc. On the other hand, permeability of concrete is the main factor affecting the durability of concrete. That is why the necessary measures should be taken in consideration to decrease to minimum levels the concrete permeability. The main factor influencing the durability of concrete is its impermeability to the ingress of oxygen, water, carbon dioxide, chlorides, sulfates, etc. When tensile stresses to which concrete may be subjected to exceed the maximum tensile strength of concrete, it cracks. The increase of these tensile stresses may be caused from different factors, but the most common of them are related to the internal volume changes. Concrete changes slightly in volume for various reasons. The most common causes are fluctuations in moisture content and temperature. Restraint to volume changes, especially contraction, can cause cracking. Cracks can occur in hardened or unhardened concrete and may be caused by some of the conditions such as plastic shrinkage, plastic settlement, structural cracking, rust, thermally induced cracking, etc. Fast evaporation of water from the surface of freshly placed concrete makes the surface of concrete shrink. Due to the restraint provided by the concrete below the drying surface layer, tensile stresses develop in the weak region, stiffening plastic concrete, resulting in shallow cracks of varying depth. These cracks are often fairly wide at the surface. Plastic shrinkage cracks can be prevented by taking measures to prevent rapid water loss from the concrete surface. Fog nozzles, plastic sheeting, wind breaks, and sunshades can all be used to prevent excessive evaporation. Because almost all concrete is mixed with more water than is needed to hydrate the cement, much of the remaining water evaporates, causing the concrete to shrink. Restraint to shrinkage provided by the subgrade, reinforcement, or other parts of the structure causes tensile stresses to develop in the hardened concrete. Restraint to drying shrinkage is the most common cause of concrete cracking. In many applications, drying shrinkage cracking is inevitable. Therefore, control joints are placed in concrete to predetermine the location of drying shrinkage cracks. Drying shrinkage can be limited by keeping the water content of concrete as low as possible and maximizing the coarse aggregate content. On the other hand, cracks are formed after placing and compaction of concrete. If concrete continues to settle over reinforcement bars, ducts, steps in the formwork, etc., cracks occur when there is a high amount of bleeding and settlement directly over formwork tie bolts in narrow columns and walls at change of depth of sections, etc. Properly designed and constructed concrete members are usually strong enough to support the loads for which they are intended. But overloading can occur for a variety of reasons. A change in use of a structure without proper structural upgrades, unintentional overloading, and other unusual circumstances. Earthquake damage is a classical example of the overloading of concrete structures. Overload damage can occur during construction when concrete has not yet reached design strength. Early removal of formwork, or storage of heavy materials, or operation of equipment on and around the structure can result in the overloading of certain concrete members. A common error occurs when precast members are not properly supported during transport and erection. Errors in post-tension construction, such as improperly timed or sequenced strand release, can also cause overload cracking. Damage caused by impact is another form of overload. A common form of impact overload occurs at slab edges of joints on vehicular traffic surfaces. Even in properly designed reinforced concrete, load-induced tensile stresses can occur. This point is readily acknowledged and accepted in concrete design. Current design procedures use reinforcing steel to not only carry tensile loads, but to obtain both an adequate distribution of cracks and a reasonable limit on cracks width. Permeability of concrete can be defined as the property that governs the rate of flow of a fluid into a porous solid. It is also related to the amount of water migration through concrete when the water is under pressure and the ability of concrete to resist penetration of any substance, be it a liquid, gas, or chloride ion. Designers of dams and other large hydraulic structures needed to know the rate at which water passes through concrete that was subjected to a relatively high hydraulic pressure. Water is generally involved in every form of deterioration, and with porous solids, the ease of penetration of water into the solid usually determines its rate of deterioration. Loss of concrete durability can be analyzed in two different aspects, such as the first one are the factors governing the concrete durability, and the second one the processes affecting the durability of concrete. Some of the factors that govern the durability of concrete can be listed as concrete mix design, structural design, reinforcement detailing, concrete cover, curing of concrete, supervision, quality of materials, etc. The behavior of concrete depends on several processes such as physical processes, chemical processes, biological processes, and others. Physical causes of deterioration can be listed as follows: abrasion, erosion, cavitation, freeze-thaw deterioration, Deicer scaling, high temperatures, aggregate expansion, etc. When a material is repeatedly struck by particles from a harder body and the surface of concrete is unable to resist wear caused by rubbing and friction, abrasion damage occurs. Outer paste of concrete wears, fine and coarse aggregate are exposed. Abrasion and impact will cause additional degradation that is related to aggregate to paste bond strength and hardness of aggregate. The most damaging forms of abrasion occur on vehicular traffic surfaces, bridge piles, surfaces in contact with waves, etc. Some of the factors affecting the abrasion resistance of concrete are compressive strength, properties of the aggregate, nature of the finishing coat, presence of areas which have been patched up, conditions of the surface, etc. Cavitation is called the formation of bubbles or cavities in a liquid. The cavities form where the local pressure drops to a value that will cause the water to vaporize at the prevailing fluid temperature. Cavitation damage is produced when the vapor cavities collapse, causing very high instantaneous pressures that impact on the concrete surfaces, causing pitting, noise, and vibration. At temperatures below zero, cement does not hydrate. On the other hand, as it freezes, water expands about 9% and produces pressure in the capillaries and pores of concrete. Exceeding the tensile strength of the concrete, the cavity will dilate and rupture. Successive freeze-thaw cycles and disruption of paste and aggregate can cause significant expansion and cracking, scaling, and deterioration. In order to prevent freeze-thaw deterioration of concrete, air entraining agent is used. Entrained air voids act as empty chambers in the paste for the freezing and migrating water to enter, thus relieving the pressure in the capillaries and pores and preventing damage to the concrete. Low permeability concrete also performs better when exposed to freeze-thaw cycles. De-icing chemicals such as sodium chloride can aggravate freeze-thaw deterioration. Osmotic and hydraulic pressures in excess of the normal hydraulic pressures are produced when water in concrete freezes. Salt absorbs moisture, it keeps the concrete more saturated, increasing the potential of freeze-thaw deterioration. On the other hand, some aggregates absorb too much water, expand and increase hydraulic pressure during the freezing of water. Also, aggregates such as calcium oxide expand about 2.5 to 3 times in the presence of moisture. Concrete disintegrates if these are in high quantity. If it is near the surface of the concrete, it can cause a pop-out. Another factor affecting the concrete durability are high temperatures. The behavior of concrete at high temperatures is influenced by several factors such as rate of temperature rise and the aggregate type and stability, moisture level, etc. Fast temperature changes can cause cracking and spalling due to thermal shock, and aggregate expansion can also produce distresses within the concrete. High temperatures also affect the compressive strength and stiffness of concrete. Above 100 degrees, the cement paste begins to dehydrate, loses chemically combined water of hydration, which gradually weakens the paste and paste aggregate bond. The effect of high temperatures on concrete is destructive. Reinforcement rods resist at temperatures of up to 500 degrees, while concrete may resist up to 650 degrees. The thicker the concrete, the longer it takes for the reinforcement rods to reach their failure temperatures of 500 degrees. Chemical causes of concrete deterioration. The chemical causes of concrete deterioration can be listed as acid attack, sulphate attack, alkali-silica reaction, carbonation, corrosion, leaching, etc. Portland cement concrete is not resistant to acids or solutions with a pH of 3 or lower. It may resist to some weak acids if the exposure is occasional. Acids react with the calcium hydroxide of the hydrated Portland cement. It forms water-soluble calcium compounds, which are then leached out by aqueous solutions. Sulfates of sodium, potassium, calcium, or magnesium are sometimes found in soil or dissolved in groundwater. These salts react with aluminate compounds, calcium, and hydroxyl of hardened Portland cement, forming ettringite and gypsum. In the presence of sufficient water, these reactions of delayed ettringite formation cause expansion of concrete, leading to irregular cracking. The cracking of concrete provides further access to penetrating substances and to progressive deterioration. Alkali-silica reaction. Alkalis such as sodium oxide and potassium oxide coming from Portland cement react with reactive silica-containing aggregates. Free alkalis present in cement dissolved in the mixing water and form caustic solutions which attack the reactive silica in the aggregate. As a product of this reaction, an alkali-silica gel is formed. This gel swells in the presence of moisture and exerts pressure on the concrete, which may lead to formation of cracks and deterioration of concrete. Concrete itself is a highly basic environment because of the strong base such as calcium hydroxide in its internal structure. The pH of the fresh cement paste is at least 12.5. When calcium hydroxide in concrete reacts with carbon dioxide coming from air or from water, it produces calcium carbonate and water, thus decreasing the calcium hydroxide in concrete, resulting in the decrease of the pH. The pH of a fully carbonated paste is about 7. When calcium hydroxide is removed from the paste, hydrated CSH gel will liberate calcium oxide, which will also carbonate. The rate of carbonation depends on porosity and moisture content of the concrete. The figure shows the measuring of carbonation depth with phenolphthalein solution. Corrosion of reinforcing steel is one of the main causes of deterioration in reinforced concrete structures. Steel is thermodynamically unstable under normal atmospheric conditions because its natural state is in the form of iron oxides. As a result, it tends to release energy and revert back to its natural state. As steel corrodes, it produces rust, which occupies a greater volume than steel. Corrosion of the reinforcement in RC structures is classified as atmospheric corrosion, chloride ion or corrosion, galvanic corrosion, and electrochemical corrosion. The internal structure of concrete is rich with calcium hydroxide, which does not have any notable effect on the strength of concrete, but it fills some of the concrete pores and keeps concrete pH above 12.5. When concrete is saturated with water, the calcium hydroxide and other soluble salts are dissolved and transported out of concrete, thus increasing the porosity and decreasing the pH of concrete. This process is called leaching. Biological causes of that concrete deterioration. The metabolic activity of microorganisms causes liberation of many acids as well as hydrogen sulfide and other corrosive reagents into environment. Algae, fungi, bacteria, etc. are some of the biological threats causing the concrete deterioration. Marine environment. Seawater is a mix of different aggressive environments because seawaters contain about 3.5% soluble salts and their pH varies from 7.5 to 8.4. On the other hand, concrete in marine environment is affected from the combined effect of chemical, physical, and biological processes such as sulphate attack, leaching of lime, alkali aggregate expansion, salt crystallization, alternate wetting and drying, freezing and thawing, corrosion of embedded reinforcing steel or prestressing steel, erosion and abrasion from waves, etc. The parts of reinforced concrete structures built in the marine environment can be classified into 3 zones regarding the conditions of environment affecting its durability. The first one is the submerged zone, which is the lower part continuously covered by seawater. The second one is the middle part called splash zone, which is subjected to continuous wetting and drying, whereas the third one is the upper part called atmospheric zone, subjected to occasional seawaters. The most endangered part is the splash zone. As a general classification, exposure conditions can be classified as mild, negligible, or low, moderate, severe, very severe, etc. Whereas EN norms classify the exposure conditions in more details, depending also on the type of environment. As a conclusion, we should be aware that the durability of concrete is a topic of very high importance for structural integrity of reinforced concrete structures. For that reason, reinforced concrete must be designed properly, taking in consideration the severity of the environment in which these structures will withstand throughout their life cycle. On the other hand, we should be able to analyze and assess the causes of loss of durability of existing structures in order to give adequate solutions to affected structures.